Okay, in our last video on this same set of notes, what we were able to do is calculate the cell potential for a voltaic cell. So we were able to see the two half reactions. We came up with an overall reaction. And now what we want to do is we want to be able to label and create a voltaic cell from this information. So the first couple things we need to know are some vocab terms. And one of those being the anode. You have an anode and you have a cathode. And the anode is always going to be where you have oxidation taking place, and the cathode is where reduction takes place. Little trick for you is that you can remember an ox and a red cat. So just kind of visualize that. Sometimes I'll put pictures up like that, but that just means that you've got the anode is where oxidation takes place, and then reduction takes place at the cathode. So if you remember those, that might help. Another way to think about it is that your vowels go together and your consonants go together. So that might be helpful. Since electrons are flowing from one part of the cell to the other, one is becoming positive and one is becoming negative. And so what we're going to see when we draw these voltaic cells is that we have to draw something known as a salt bridge. And a salt bridge is just any sort of soluble salt. Typically, sodium nitrate would be a common one that's used. There's all sorts of them, potassium nitrate, any sort of soluble salt. And the reason we need a salt bridge is because we need to be able to maintain that charge neutrality. So let's see what all this means. Here we're going to sketch our cell. I reminded us of what our overall reaction is. In fact, I can even do my two half reactions as well. I can see that we've got, I guess I could do, let me do the unbalanced. Let's just say we've got Cu plus 2 going to Cu. We see that right there. And then we've also got Fe going to Fe plus 3. So when we went through and balanced this, what we ended up doing eventually, and maybe I'll just continue with this then, just to remind us on this one, we had a 3 here and a 3 here. We had a 2 here and a 2 here, which meant that we had to have a plus 6 electrons for that first one and a plus 6 electrons for this one. So when we go through and draw a voltaic cell, we are going to want to show that there are two half cells, and we show two containers for these half cells. So this is how we draw our voltaic cell. We're going to have electrodes in each of these cells. So these are pieces of metal. And we can just go ahead and arbitrarily assign them. It doesn't matter which one I put where, but maybe I'll look at my first one and I see that I've got copper in the first one, so I'll just write that on that one, and I'll put iron on this. It is going to be the solid that gets labeled, so you're not going to do the ion there, but the solid, so Cu and Fe, which means that in solution we've got copper 2 ions right here, and we've got iron 3 ions in this one. So now we have this is all set up and connected to a voltmeter. Our electrodes are attached. This solution in this container, those are our ions that we've got. So if we were to read the maximum voltage that this cell would produce, if you look back at the top of your notes, you're going to see that we calculated it was 0.38 volts. So we did that with our reduction potential tables. And the other thing that we need to add in here, remember, is that we need to be able to maintain that charge neutrality. So we need a salt bridge. And this is just some sort of porous membrane that allows the solution to flow there. So if we were to use something like sodium nitrate, I'm going to have some sodium ions and I'm going to have some nitrate ions. So that's an example of what we might use. So now we can start labeling some things. We read through our notes and we saw that the anode is always the electrode where oxidation takes place. So I can look back at my half reactions and I see in copper I'm gaining electrons, so that's where reduction is taking place. And with my iron I'm losing electrons, so that's where oxidation is taking place. So as far as our copper, we see that our copper is where reduction is taking place. So I can just go ahead and label that right here. And iron is where oxidation is being oxidized. So I can label that one as well. Um, I know that reduction always occurs at the cathode. I know that oxidation always occurs at the anode. I know that I can remember that we've got cathode and anode. This I'm not labeling, I'm just making a little side note right here. So just a reminder that cathodes are positively charged, anodes, that N for negative, are negatively charged. So that was just a little side note for us. That means that at the cathode, this is going to be positively charged, and the anode is going to be negatively charged. It's that way every single time. And then we can also talk about what's going on in our cell now. If we've got our copper is our cathode and our iron is our anode, another thing that we can remember is the term fat cat. And what that tells us is that the electrons always flow from the anode to, there's our fat, to the cathode. So there's our little reminder. It's electrons always flow from the anode to the cathode. So we should label that in our diagram of our voltaic cell. And here's our anode over here. So the electrons are going to flow in this direction. If you were to try and verbalize this somehow, you would never say that they flow from right to left, or you would never say that they flow in a counterclockwise position, because that's not really correct. You could look at it from the other side and that would not hold true. So you can't use those words when describing it. You have to say that they would flow from your iron to your copper in this example. Well, if that's taking place, think about how all of these electrons are now, if we've got these electrons flowing in this direction, all of a sudden these electrons are gathering over here on your copper. So you're getting an excess of electrons there. Who likes to hang out with negative particles? Positive particles. So these copper 2 ions look at this and say, whoa, there's an electron party going on right there. Let's go ahead and jump on. So what happens is that the size of this electrode is going to grow. So this electrode ends up getting bigger. It increases in size. In that, during that process, we see that the solution is going to decrease in amount because all of those ions are precipitating out of solution. So solution decreases. Maybe you want to remember that this gets bigger, this electrode gets bigger, and that happens to be the positive charge. Maybe just that little reminder is helpful for you, seeing the positive charge and this gets bigger, but you should be able to reason that out as to why that happens. Well, we just said that this is going to decrease in size. Your copper 2 ions are going to decrease in amount, your solution. So what that means is that those get replenished with your positive ions from your salt bridge. And we're going to see that that whole situation is the opposite case on the anode side. And so since you are losing electrons from your iron, what ends up happening is that the iron is going to go into solution, and so this is going to, use blue, this is going to become smaller. It's going to decrease in amount, and this solution is going to increase in amount. And again, because we're losing these electrons, we see that we need to have our salt bridge, the negative ions from our salt bridge are going to have to replenish that, so those nitrate ions go towards the anode. And I think that covers it for what we would see in that cell. I'm going to go ahead and do the next example. I think we've got it all covered there. The next example, you're supposed to flip over and do on the back of your notes. And we see our shorthand method, so let's remind ourselves of that. We could either write something the long way, or you can write it the shorthand method, so that we have our oxidation half on the left and our reduction half on the right. So when we go through drawing this, I guess a couple things that we might want to do. Maybe, let's see, let's first start drawing our cell and give us, we've got our cell right here. We're going to have some electrodes that are hooked up to our voltmeter. So this whole thing is immersed in a solution of ions. So now if we were to label these, I'm just going to arbitrarily call this one aluminum and this one manganese. And that means I've got aluminum ions in here and manganese 2 ions in here. So now, probably the best thing to do now would be to go ahead and do our half reactions and figure out our voltage. So we know that we've got, it tells us, remember that in this shorthand script here, we've got it told to us as to what's going on, what our half reactions are. This is my oxidation half with my reactants and products. This is my reduction half with my reactants and products. So you write it just in that order. So you've got aluminum going to Al plus 3, and you've got Mn plus 2 going to Mn. And then you go through the balancing act. And this is going to be 2 electrons. And of course we have to multiply by 2, multiply by 3. And what we end up getting in this case is, let's see where I can write it. We get 2Al goes to 2Al plus 3 plus 6 electrons. And then 6 electrons plus 3 Mn plus 2s goes to 3 Mn's. And your electrons cancel out, and then we could add up that whole thing and get the overall reaction in case you were asked for it. The overall reaction. Hopefully this is going to show up on the screen. Okay. So it goes to 2Al plus 3Mn plus 2 yields 2Al plus 3 plus 3Mn. So there's our overall reaction. So in the process, one of the main reasons we wanted to do this was to be able to come up with our voltage. So you look at your reduction potential table, and you see that your reduction half, which is right here, this is your oxidation half. What you see for your reduction is that it's a negative 1.18. For your oxidation half, you don't see that, but as a reduction half, it's a negative 1.676. So you flip it, and it becomes positive 1.676. You add all of that up, and your cell potential becomes 0.496 volts. It's positive. Remember, we made it positive. That was purposeful that we did that. So 0.496 volts is the maximum voltage we could get out of the cell. So now we can start labeling things. And with this, we see that our positive, hold on one second. Okay, so sorry about that. So now we are looking, we're going to label, and we have our aluminum we see was oxidized, so this is our oxidation half. We see that our manganese was reduced, so this is our reduction half. We know that oxidation always occurs at the anode, and the anode is negative. And we know that reduction always occurs at the cathode, and the cathode is positive. So if you were asked some other questions, what we haven't done, of course, is shown our salt bridge. We need to draw that in and think about what's going on with those ions. It could be sodium nitrate, it could be potassium nitrate. Let's do potassium nitrate. So what is going to happen is that your electrons are going to flow from your anode to your cathode, so your electrons flow in this direction. And in the process, the manganese, that's where the electron party takes place, so all of a sudden those positives are going to want to jump onto that, and this becomes bigger. Therefore, this one becomes smaller. The manganese becomes bigger because those ions, the solution, decreases in amount. And it's the opposite, your aluminum ions, it increases in amount. And so as far as replenishing, since we're losing electrons from our aluminum, the nitrate ions need to replenish that, so we need our negatives going in that direction. Our positives need to replenish on this side. So I think that covers everything. That should do it. That's how you draw voltaic cells.